We've talked about distributions, means, standard deviations, standard errors, effect size, z-scores, that sort of thing. Today we're going to talk about statistical significance. What is it and how does it work? Some keywords that we need to keep in mind: the null hypothesis, alternative hypothesis, p-values, statistical significance, t-test, effect size, clinical relevance, and statistical test. What do we mean by statistical significance? This is probably one of the most confusing or confused, conflicted, controversial concepts that there is in statistics. Let's start out by talking about the null hypothesis. What is it? It's not reality. Null hypothesis is it's a statistical test. Anytime you do a statistical test, you test the null. And the null is this situation in which there's absolutely no difference between groups. They are the same. You're selecting essentially from the same distribution going into both groups. Some meanings: the difference between groups is not greater than would be expected by chance. Means come from populations whose distributions are identical. The treatment has no effect on outcome. A null hypothesis is a fictional, well, it's not really fictional, but it's a concept where there is absolutely no difference. And that's the statistical test that we're doing. That's the hypothesis. We don't test if groups are different. We test if they are not different. You can only reject the null hypothesis or fail to reject it. You conclude the differences are unlikely by chance alone. If you do not reject the null hypothesis, you have not proven that the groups are the same. You have just not been able to show they are different. You cannot accept the null. You cannot prove no difference. This is a very important concept. You reject the null or you don't. Those are your choices. You have this null hypothesis. You're not testing if something is important or different. You're just determining if your results are reasonable, if the null hypothesis is true. So you're doing a test and you're going to compare it to nothing, to no difference. That's what a statistical test is. You may not like that. It may not make a lot of sense. But that, in fact, is what it is. Now, we're going to promote the idea that hypothesis testing is a two-stage process. In number one, you eliminate chance. We're calling null hypothesis chance as a reasonable alternative, i.e. statistically significant. That's what statistical significance means. It means that you've eliminated chance as a reasonable alternative. Once you've done that, then you can go on to determine if the non-chance difference is clinically relevant. Most papers stop at the first step and don't talk about the second too much. And if they do, they talk about it only in the sense that they say, well, my results were statistically significant, therefore it's implied that they're clinically important. Nothing could be further from the truth. We have seen how to determine effect size. That's the difference between two means divided by their average standard deviation, which gives you a difference in standard deviation units. The t-test, which we get a t-score and then see where that t-value falls in a null probability distribution. In other words, we look at that t and see where it's placed in a distribution of no differences. Now, how can there be a distribution of no differences? I mean, it's zero, right? Well, no. There's a distribution because there's chance. We are estimating the means. We're estimating the standard deviations. So we're not really looking at the true underlying population. That population has a distribution, and we're particularly interested in the distribution of the null hypothesis, which says the underlying population has a zero difference of means, and it's divided by the average standard deviation of the population. Now, if we look at this formula for the t, we can see that the numerator is similar in both effect size and t-test. It's the same. It's the difference between the means. The denominator, however, on the effect size is the average standard deviation. Now, hopefully you may recognize that the standard deviation squared divided by n, square root of the standard deviation squared divided by n, is the standard error. That's just another way of writing a standard error. And rather than averaging them, we sum them up. That's just a factor of the distribution of t's, which have a slightly bigger standard error than the average standard deviation of the two groups. Now, when we talk about a significance test, we look for the critical value, and that's a t-value that the probability of finding that t or some value greater than that is less than 0.05. We'll see an example of this in a second. The critical value, or the default starting point for effect size, is that it has to be greater than 0.5. So p is less than 0.05, effect size is greater than 0.5. In the t-test, we reject the null hypothesis, or we don't reject it. And we can't accept it. We're not proving it. We can either reject it. And if we do reject it, then we determine what's the effect size for our clinical judgment. If we look at the formula for the t-value, we notice that as n increases, that denominator is going to get smaller, so t gets bigger. So the t-test is dependent on sample size. The effect size is not dependent on sample size. The denominator is in terms of standard errors. The effect size is the denominator is in terms of standard deviations. The denominator in the t-test is considered the standard error of the differences. And we use standard errors when we're looking at populations of infinite populations, in this case an infinite population of the differences between means. And we divide those by the standard error of the difference to get an infinite distribution of t-values. And then we look to see what our one sample where it fell out. Effect sizes are based on our best estimate of observation in terms of standard deviation units. So, statistical significance, the p-value. Anytime you collect data from random samples, the means or other estimates are very unlikely to be the same, even if the underlying populations are identical. The test assumes the null hypothesis is true and then determines by known statistical theorems if the assumption is reasonable. That's what we're testing. A t-test or a p-value is giving us the probability that our assumption that the null is true is reasonable. If it's a very low p, we reject that assumption. We reject the null hypothesis. If the results are unlikely to be found by chance, then we say there is a statistically significant difference. It is quite sad that the word statistically significant has been confused by the population of investigators, by many of them, to assume that means clinically relevant. And we're going to keep nailing on that point. A small p does not mean relevance. If the results are outliers for null distribution, then we reject the null and call it statistically significant. P less than 0.05 is an arbitrary conventional cutoff. So the definition of a p-value, it's the probability of finding a test statistic, for example, a t-value, that is as great or greater than a value would be if the null hypothesis was true. This is an awkward sentence, but that's what it is. Let's see if we can clarify this a little bit. This is a noisy slide. I encourage you to look at this slide and study it and kind of understand it if you can. Let's take a look and relate it to what we've seen before. So this graph up here is the distribution of normal intraocular pressures. This is from the Beaver Dam study, and we talked about it a couple weeks ago. So the red is the normal, and the blue is those with glaucoma. Now, if you fall out here, remember, you're not very likely to be a normal person in terms of IOP. And so if your IOP was greater than 22, we would say that you are unlikely to be in the normal population. But you still could be. I mean, you could be a value out here. We have seen also that a person with glaucoma may very well have an IOP of less than 22. So let's think now of this in terms of, let's move our analogy over to a t-distribution. Now, here we have t-values. They go from -5 to +5, actually higher than that, but the mean of the null distribution is 0. Because the t-test, remember, the numerator is the mean of group 1 minus the mean of group 2. And so if there's no difference, the mean is 0. But these are samples, so not everybody is 0. If 0 is true, not everybody has a 0. There is a spread. And that's the whole point of the statistical test. I mean, if you just ran a study and saw that it wasn't 0, you could say, hey, if you knew that 0 was always going to be the answer, if the truth was 0, then you wouldn't need to do a statistical test. The problem is that you have randomly sampled, and so there is chance variation. So if we look at this red distribution, these are all numbers. These are all t-values that you could get. If you did this test an infinite number of times, this is the distribution of the t's that you would get. Most of them would be at 0, but there's an awful lot, in fact, many more than the 0, that are not on that 0 point. And if the t-value exceeded something a little bit greater than 2, then we would say the null hypothesis, let's say it was right here. Well, we would look at this probability density under here, the number of people, or the number of t-tests that are beyond 2. That's the portion we would say is really, it's possible to be out here, but we're going to say it's unlikely that your null hypothesis is true. Even though these are perfectly reasonable values when the null hypothesis is true, it's just that it happens so infrequently that, well, 5% of the time, that we're just going to say, we're going to reject the fact that the null hypothesis is true, and we're going to go more with the likelihood that the blue, which is just this one arbitrary, we don't have any idea what the true alternative is. This is one possible case. So what the statistical test does is it says, okay, this is what the distribution looks like, the distribution of t's, if the null hypothesis is true. We're going to look at our individual t and see where it falls in this distribution. If it's outside of this 2 criteria, we're going to reject the null hypothesis as being the most reasonable alternative. It's going to be more likely to be not the case that the null hypothesis is true. But what happens if it's less than 2? What happens if it's a number in here, just a little bit less than 2? Well, we don't reject the null hypothesis. But that doesn't mean that the null hypothesis is true because we don't reject it, because if the truth was really this distribution, and this is the distribution of t's given the truth in a situation, in this particular situation where the null hypothesis is not true, in fact the means really are different, then they could look like this. Well, if we don't reject our null hypothesis, we can't conclude that the null is true because you have all these cases where you're not rejecting, you're not saying it's different, but in fact, underlying it really is. You just don't see it. You don't detect the difference in the study that you've done. All right. So these can be probability density distributions, and the probability that's under here. It's like in our glaucoma case. If you're greater than 22, you could be, it's possible that you could be normal, but we're just saying that you're not really likely to be normal because not very many people fall outside of 22. But similarly, if you're less than 22, we're not saying you're normal because a lot of glaucoma people can be less than 22. All right. The p-value does not inform on the size of the difference between the means. I mean, I'm saying this over and over again, but I hope you're getting the idea. A tiny p does not mean important difference. Let's take, for example, our single vision lens versus PAL study. The p there was 0.004, a very small p-value, highly statistically significant, but not clinically relevant. The p-value is a function of the size of the difference between means. The variability of the sample and the number of subjects is a poor measure of the magnitude of effect. The p-value only determines if the null hypothesis is unreasonable, not if it is true, if it is unreasonable. You're going to hear a lot of people over the course of your career, when you go to conferences, when people are talking about their studies, and they're going to say, oh, look at this, my results are statistically significant. That means that their groups were different beyond the likelihood of chance. But they're kind of implying that they were important. So I just say smile quietly to yourself when you hear a person say their results were statistically significant and they mean it in the sense that the results were clinically relevant. Now you know that is not necessarily true. Their results may be clinically relevant, but not because their results were statistically significant. They can also not say their results were clinically relevant because they found a big difference when the results were not statistically significant. And that happens when you don't have very many subjects. So they didn't have time, or they didn't want to take the effort to run very many subjects. They found this big difference and they say, hey, look at me, I found this big difference. But if they run a statistical test and the results are not significant, the way random variability is, chance is still a reasonable alternative, no matter what the size of the results they found. If they're not significant, they don't eliminate chance as being a reasonable alternative. All right, in our last homework, we looked at Restasis. It was the study where there was a comparison of vitamin A and cyclosporin, eye drops for the treatment of dry eye. I like this paper. I like this paper because it's a good example. First of all, I want to say about the paper, one of the questions when you're starting to look at something is there likely to be any bias in the results? Was it sponsored by a drug company, Restasis, or somebody else? No, this study was done in South Korea by a college of optometry, basically, a university medical place. And they had no apparent bias in their results, in their analysis. They did a nice study in the sense that they randomly assigned the patients to the three groups. Now that was a good move. They tested the difference between their subjects. First of all, you can look and see, does your patient, if you're reading this paper to see if your patient applies, is it somebody who would fall within the bounds of this particular study? Now, these people tended to be, I'd say, between 20 and 60 years old, based on the age of the age distribution given in Table 1 here. They were pretty evenly divided in terms of gender. Then it gave tear film, Schirmer. You know, one thing that was kind of disturbing about this table is there was a subjective test of blur that they did not include in here. I was disappointed to see that because it made it impossible to calculate effect size on that. It was a little annoying. Let's look at that. Okay. All right. Now you've seen that if the demographics fit, then you can go on and look at stuff. Now, can chance be ruled out in comparison between intervention and control? Actually, that was what was kind of interesting about the way they presented the results. They looked at everybody with respect to the control group, which just got regular old dry eye, or not dry eye, but just drops. Simple drops, not meant to treat dry eye. They do a test where they ask, is there a difference between, well, first of all, let me point out, these are changes from baseline. They are not, they're not the actual means, but they look to see if there are changes. And here we see the change towards the change to a better score at 3 months is actually better in the vitamin A group than it is in the Restasis group, but in terms of the raw numbers. But they claim that in their analysis of these values, there was no difference. Now, I'm pretty convinced that if they had done the proper statistical analysis where they adjusted for baseline values and then compared directly the post values, they would have found significance in some of these. I mean, you can just see how the standard error bars are far, far apart, and they're not significant. They're saying they're not significant. But they are saying that there is a difference. For example, here they're saying the vitamin A was significantly different than the control. They don't say the vitamin A or the Restasis is better than control at 2 months, but Restasis takes 3 months to work anyway, so at 3 months it is better than control. I think personally, I think they were negligent in not comparing and talking a little bit more about the comparison of the two groups. But we ruled out chance. Now let's see what our effect sizes are. So we have baseline For Restasis on the Schirmer test of 393 and 367, you guys did this. If we look at the Restasis versus vitamin A, the difference minus 0.83, the average standard deviation, we have an effect size of minus 0.48. That's almost the half standard deviation that we use as a criterion. When we look at vitamin A versus control and Restasis versus control, we find very large effect sizes. So both drugs worked. But my question is, if Restasis costs between $300 and $500 a month for the rest of your life, insurance doesn't always cover that. I know at Pacific University for employees, their insurance does not cover Restasis. So that's a $300 to $500 a month charge that's tagged on for the rest of one's life. Even when they're in retirement, you're still going to pay that. That's a lot of money. There may be Medicare drug things that bring down the cost a lot, but still, to the economic community, that's a lot of money forever. Restasis, on the other hand, or vitamin A, on the other hand, is $15 to $35 a month. Now that's a much more reasonable amount. And I think if I was going to, I'm concerned that the authors treated Restasis and vitamin A as equivalent. You have to think about other things. You have to think about cost. Now, there wasn't a statistical significant difference in adverse events, but if you look at Restasis, 5 of the 50 people dropped out due to adverse events, whereas only 2 dropped out in the vitamin A group and 1 in the control. Now, that's not statistically significant, but it's also not giving a reason to hang on to Restasis as a reasonable alternative. I just don't understand why the authors did not talk about vitamin A as an alternative. Why is vitamin A not used? So I'm wondering, do you think a vitamin A rich salad with omega-3 dressing could work as well? I don't know. It's not going to be sponsored by a drug company, I can guarantee you that. But it's a question that I think should be tested. Okay, so far in this semester we have looked at searching the literature using PICO, Population Intervention Comparison and Outcome. Excuse me. We assess bias, favor randomized control trials and or meta-analyses. We select papers where the subjects match the profile of our patients. And we look to determine if the results were significant or non-significant. That is, do they eliminate chance based on the p-value? And if they do, what was the expected benefit? Clinical relevance, what was the effect size? So these are the things that we looked at for the first half of this class. For the midterm, I suggest you study lecture slides, listen to podcasts, go over quizzes, know how to compute these various tests, know rules of thumb. You need to understand the concepts, not just plugging numbers into formulas. That's not going to help you that much. Know the meaning of the p-value. Practice computing effect size and confidence intervals when reviewing the literature. All right, that's it.